Hello again, Year 11. Today we're going to be looking at Gay-Lussac's law, starting with the man who came up with the law himself, Joseph Gay-Lussac. On the left-hand side here, you'll see a portrait of the man's face, and on the right-hand side, you'll see the kind of observation he took note of, which is related to temperature and pressure. If you look at our steel drum here, this just gives you a nice little introduction of the Gay-Lussac law. Let's look at this. What happened to our steel drum can in this animation? Well, we can see firstly we have the water hose spraying on it, so the water on the can, and then we can see that the can ends up falling on itself. It compresses on itself, so the drum is compressed by the water, it almost seems. But why is that the case? Well, let's have a look. Now, when we have a look at this in terms of whether temperature has increased or decreased inside the can, we are spraying the drum with room temperature water from the hose, so we are seeing a decrease in temperature. And what we know is when temperature decreases, the overall kinetic energy of our particles decrease. So the air particles inside the can, that kinetic energy is decreasing. They're not as energetic. They're not really pushing against the surface of the can at the same magnitude as it was when it was at a really high temperature. So we have a lower pressure system in the can, and then we have the same pressure system being exerted from the outside. So if it becomes lower inside and becomes higher on the outside relative to that change, then that pressure from the outside air essentially condenses and compresses the drum into a smaller size. So what can we say? We have lowered the pressure because there's a lower temperature, and that has led to the compression of our drum. If I want to show the relationship between pressure and temperature, I can use my trusted simulation. So on Gay-Lussac's law, we are coming up with the idea that volume stays constant, so the amount of space the particles can occupy stays the same. The amount of particles that are available in this system is also the same. I said that a decrease in pressure leads to a decrease in temperature. And if you look at that, 1 atmospheric pressure, 298 Kelvin, 0.6 atmospheric pressure, 179 Kelvin. So there is a trend that by decreasing the pressure, there is a decrease in temperature. If I did the opposite and I increased the pressure, and I did it again, you see it's just increasing along with pressure. So if you just have a look at this data points being plotted on the graph, you can see you can actually make up a linear plot for this. So if I draw it on something I did earlier, and I do not too bad of a straight line, I can see that there is a linear trend between pressure and temperature. And what that essentially tells us is if you have a linear plot or you have a straight line being plotted between two variables, so pressure and temperature, that would imply that the pressure and temperature of our system is directly proportional to each other. So if I increase pressure, I also increase temperature. Remembering that volume needs to stay the same in the entire system. If you want to have a look at Gay-Lussac's law as a demonstration, this will be the video I'll be showing you from the side, guys, and that will be included in the comments below. If we want to look at a general application of the Gay-Lussac's law, then you'd be looking at the application of firing a gun. Now remember, when gunpowder burns in the gun, so when you're burning gunpowder, you generate a significant amount of heat. That heat energy, that heat energy from that burning of gunpowder excites the gas particles in the gun. So if it becomes excited, there's more kinetic energy for our gas particles, and that leads to an increase in temperature. So now that our gas particles have an increase in temperature, that means, according to what we said with Gay-Lussac's law, an increase in the temperature will lead to an increase in the air pressure inside the nozzle of the gun. So we have a higher pressure of hot gas. And it's that pressure that essentially forces the bullet out of the barrel. Obviously, you need a little bit of Newton's third law, but that's also the science behind how the gun works. If we try and look at it in a simple formula, we're saying the Gay-Lussac's law is the pressure of the amount of gas held at a constant volume would be directly proportional to the temperature in K. So we're saying that P is directly proportional to T under the conditions that volume stays the same and the number of moles we use stay the same as well. K is still constant, so there's no units, and because it is a constant, if you change the pressure from system 1 into the second system, so if we see a change in this, then we can do a calculation to find the new temperature of the system. And that's the value of having K as the constant there. It allows us to note that basically the ratio between pressure and temperature will stay the same after the change has occurred. And so we can find the second variable, what the unknown for that would be. Temperature is in Kelvin. Pressure is measured in kilopascals, and like I said, the constant has no units. If we look at some calculation questions, which we have here, some hints are also provided and formulas to use. What I'm going to do is skip over to the answers and explain them in 5 seconds, so you have been warned. Pause the video now. Alright, so let's move on to the answers. And this is the formula we have. P1 over T1 equals to P2 over T2. Remember, the subscripts just mean which new system it's in. It's in the second system. This number 1 was our original. If we look at T1 is the 283.15, 0.95, that's our P1, and 0.75 is our pressure. So what we're looking at is temperature T2. Rule number 1 when it comes to doing calculations in chemistry or physics is just substitute the numbers into the formula. So there we have that. If you might be wondering why we need to substitute numbers first, when in maths you do the opposite, you rearrange it. You get marks for correct substitution. So just try and maximize the amount of marks you can get. And so we have T2 as the subject of, or T2 as the thing we need to find. So if we try and make T2 the subject of the equation, T2 is equal to, if I just swap the two equations around, so I just flip them on both sides, be 0.75 equals to 283.1 over 0.9. So all I have to do is times both sides by 0.75, cross it out, times it by 0.75, and I get the following working out. And so the answer I get, if I plug it into my calculator, is 223.54 Kelvin. But the question is not quite over yet because we need to convert this into degrees Celsius. And to do that conversion, you have to minus Kelvin, your Kelvin value, by 273.15. And what we end up getting is minus or negative 49 degrees Celsius. All right, now let's look at question 6. Question 6, we're also trying to find T2. So we're still trying to find T2 as well. This time we have a slightly different pressure system. Don't worry about doing any conversions for this one because it's just using the same unit, so we can stick by that to keep consistency. The initial temperature is 20 degrees Celsius. Okay, you need to convert that into Kelvin, so you need to add 273.15. Okay, same idea, trying to find T2. So again, do your substitution, you'll find it looks like this. Okay, and we get an answer of 337 Kelvin. If I then subtract it by 273.15, I'll find that in degrees Celsius, T2 is 64 degrees Celsius. So we've come quite a bit in terms of the gas laws. We initially talked about Boyle's law, which is saying that when temperature and number of moles are the same or aren't changing, then the pressure is proportional or inversely proportional to the change in volume of a gas system. In Charles' law, we said that the pressure and the number of moles stay the same. Same old, same old. When that happens, then the volume is directly proportional to temperature. In Gay-Lussac's law, which we just talked about, if volume stays the same and the number of moles stays the same as well, then pressure is directly proportional to temperature. And those are the three laws we came up with based on what we learned from the experimental data from the simulation and also from the videos that we've seen. Okay, so if we try and combine these three together, so we have Boyle's law, which looks like this, equation 1, Charles' law, which looks like this, equation 2, Gay-Lussac's law, which is equation 3. If you combine equation 1 with any of the equations 2 or 3, you'll come up with the combined formula of PV over T, again still equal to K. Or if you're looking at two changes in the same system, you can rewrite it like so. Remember the subscript numbers we have here, just designate the initial and final, being 1 is always the initial condition of the system, and 2 is the final condition of our system. Alright, so if I try and write that down, P1 V1 over T1, P2 V2 over T2. Pressure in kilopascals, volume in liters, and temperature in Kelvin. Okay, so we need to try and work out what the final volume of our sample is for question 7. And in question 8, we need to find the new pressure if the volume has been increased. So using the formulas we just used or discussed, which is the one over here, we substitute the numbers in first. So V1 is our sample. Remember, volume is in liters, so you need to convert 153 milliliters into 0.553 liters. Temperature needs to be converted into Kelvin, and so you need to add that number by 273.15. Pressure you don't need to convert, and then the sample temperature T2 needs to be converted into Kelvin. Pressure 91 doesn't need to be converted either. So if I loop on, I just essentially rearranged it so that V2 is the subject of my equation. I'll find the following answer holds true. So the volume is equal to 0.65155618887. So that's the total volume. If you look at the significant figures of this question, the small significant figures available in my question is 2, so I need to round this number off to 2 significant figures, which is roughly 0.56 or 65 liters, sorry, so 0.65 liters. Go about it the same way, 25 degrees Celsius, 200 degrees Celsius, both those numbers need to be converted into Kelvin, so anything to do with temperature needs to be converted in Kelvin. And I'll find the following numbers. Okay, so P1 is this one over here. I have T1 over here. T2 is this number here. V1 is over here. V2 is here. I'm trying to find the new pressure, which is P2. The answer I find is 117. Just checking through the significant figures in the question. The lowest significant figures I used was the 25 degrees Celsius. So you would have to convert that into 2 significant figures, kilopascals right there. Now some of you might say, well, I did convert the degree Celsius into Kelvin. So if that was the case, what would be there for the question there? You know, if you converted it from to Kelvin, then use the significant figures available, and you'd still find overall, if anything, it's still 3 significant figures, so it doesn't actually change the overall round-off answer we have here. Okay, so that is the answer to 8. And that essentially concludes the calculation section and what we've done so far. We've looked at Gay-Lussac, and we've also looked at the ideal gas law formula. So we've looked at the ideal, or looked at the combined gas law formulas. Okay, and that essentially sets you up to do the next law, which is Avogadro's law. Until then, take care and stay safe.
And that concludes our lesson today about Gay-Lussac's law. So we've covered the 3 gas laws. In the next recording, we're going to be looking at the combined gas law and also molar volume. So until then, see you next time.